Okay, hello everyone. Let us continue with the convexity part that we were doing last time. We saw tailored expansion of an infinitely differentiable function, and this is what it looks like for a function that goes from Rn. Okay, let us say from R to R. So for functions like this, we have the tailored expansion. So I can expand the function fx at the point x equals to a using this infinite series. Okay, so how many terms I take will tell us how good is our how close are we to the function approximation around a. Okay, so this is an approximation around a. Okay, not everywhere. So this is the formula that we remember, and then we saw some examples where we saw how to expand e to the x at x equals to 0. So here a is 0. And we saw how we can expand sine x also, let us say at x equals to pi. So we can apply this formula. And here this denotes the first derivative, this denotes the second derivative of f with respect to x, and so on. And then similarly, we can do other expansions. So I told you last time how to do this at x equals to 0. And if we do this, and if we stop at the first two terms of the Taylor series, then our approximation of the function will be 1 plus x at x equals to 0. So at x equals to 0, which is this point here, we can approximate the function using first order approximation. So this will be just approximation by a line at point x equals to 0. And if we had gone further and also included the third term from the Taylor series, then we would have a quadratic approximation because there is a power here. So at x equals to 0 again, so which is approximation somewhere here. So it is slightly bent now. Okay, so this is slightly bent. So this is the blue curve that we are talking about. Is the approximation, and this is the original function e to the x. So we can approximate e to the x at x equals to 0 via this quadratic. Okay, and then similarly we can expand e to the x as 1, and this is how it will look like. So if we stop at first two terms, then this will be this. If we stop at first three terms, then we have this, and four terms, and so on. So this way our approximation gets better and better to the given function e to the x. Okay, so I hope you can hear me. I hope.
Yes, sir.
Yes. Okay.
I'm audible. So I have a doubt. So
yeah.
We said that convexity, we can say the convexity is equivalent to the fact that the first order approximation should be the global estimator, should be the global underestimator of the function.
Yes.
So if we consider an extended function, so we said that the convexity will be maintained if we form an extended function or something else. So
of a convex function, yes.
Yes, sir. So if we see for the range, so domain outside the original function's domain. So suppose the domain is defined a to b, and we see at b plus c something, or c positive. So there the slope will be 0, and that would be infinity plus 0. But that would be an overestimator or something like that, right? That won't be underestimated.
What exactly is your function? Can you tell me? I will write it down.
Okay, so let's suppose from a to b it's x square, and after that we have extended it so that for the rest of the range it is infinite.
So a to b it is x square, right?
Yes, sir.
So and then okay, and then you want to extend this by the extended function, right?
Yes, sir.
Yeah, so x square graph, how does it look like? It's like a parabola.
And then infinity, left and right.
Yeah. So after beyond this point, which is let us say B, and let us say this is some A, and after that it's like infinity, right?
Yes.
So it does
So
not violate
after,
convexity, right?
yeah, but after B, we have got gradient of f of x equals to 0,
Yeah,
because now it is a constant.
but I did not say that the first order convexity only applies when the function is differentiable, right?
Okay, didn't know that.
So in this case, the function is not differentiable, but still it's convex. So we prove this via the first definition of convexity, that any arbitrary line joining these 2 points will be above the curve, right? So the first order convexity applies when the function is differentiable, right? In this case, it's not differentiable at A and B, like you said, but that doesn't matter. That doesn't violate that it's not convex, right? Because our original definition still works. First order convexity only applies. It's an easier way to check sometimes when the function is differentiable. Okay. Okay. So so we were doing this Taylor series, and then we can expand sin x also, and then sin x. The reason why I am doing a little bit of Taylor series is it's a very big hammer. So when you are like when you are working on something in each field, you have certain good hammers that you keep using it. If you are a signal processing guy, you will keep using Fourier series and Fourier transform and so on, Laplace transform. So the hammer is there is this, right? And in data science and so on, calculus and linear algebra. And one of the most important thing is Taylor series, because it can approximate arbitrary functions locally, but still it can approximate it pretty well. So it's a very big hammer. So it's a good idea to understand Taylor series. And it will play a role, obviously, in higher order algorithms. If we are deriving, let us say, if you want to derive Newton method, which requires Hessian. Hessian is like the higher order derivative. So you will get a clue of why we are doing that. Okay, so why are we interested in Newton method in some cases? And the point here is that higher and higher derivative you can do, and better curvature information you get. And better curvature information you get, better decision you can take in moving towards the maxima or minima of your loss function. So that's why it's important. Okay. Okay, so this is the Taylor series approximation
Sir,
of the yes.
yeah, I have a question. Like, I don't know if it's right or not. So, if we take Taylor first order of approximation, whether it
Yes.
can be a supporting hyperplane, like supporting hyperplane also does that. Like, it will because we are underestimating, and at some like some half, it will be all the points
Yeah, exactly.
in, yeah. So it is it
Exactly. That's the point. Like that's where we are going.
okay.
So first order Taylor approximation is becomes a supporting hyperplane, and it becomes if it becomes a global underestimator at each point in the domain, then the function itself is a convex, because each time you draw a tangent, and then it's always on the, let us say, on the left side of your hyperplane. That means that left or like up, whichever way you imagine. So then it becomes a convex function. So it is a supporting hyperplane because, yeah, it is approximation the function by a plane in the smallest possible region you can think of. So it does become supporting, but the problem here is that if you see the definition of the supporting hyperplane, the side your set should be on completely on the one side. Okay.
Right.
So this may not be true for all types. So supporting hyperplane was defined for sets, first of all. Okay, we did not define supporting hyperplane for functions. Right now we are dealing with functions. You can relate a bit, but you can relate, let us say, with the epigraph. Okay, so epigraph is the area above the. It's like you consider epigraph, then you consider all the points above the graph of the function. So this is your graph of the function. So let us say graph of f. Then epigraph is a set of points above this. So now you can talk about supporting hyperplane for a set. So if it so happens that each Taylor approximation becomes a supporting hyperplane of the epigraph, which is the set of the function, then it's a convex. And there is a relation that if epigraph of f is convex, if and only if f is a convex set. Okay, so there is a relation between the convex set and convex function. So this is a convex function. So all these things are related. Okay, so if a function is convex, then epigraph is a convex set. If epigraph is a convex set, then at each point the tangent that we draw, which is nothing but the first order Taylor approximation, that becomes a supporting hyperplane. So all these are equivalent statements. Okay, but as I said, supporting hyperplane, a hyperplane is a supporting hyperplane when the whole body of the set is on one side only. Okay, for all the points you are always making obtuse angle with the normal to the plane which is here. So that must be satisfied for a plane to be a supporting hyperplane. But there are cases where it may not be satisfied if the sets are like this, as I said before. So if I tell you to make a supporting hyperplane here, you won't be able to make, because there is no possible way to make a tangent plane such that whole body of the set. So I cannot draw such that whole body of the set is on the left side or on the right side. In this case, there is always some part on the left and the right. So I cannot draw supporting hyperplane here. But it doesn't mean that I cannot draw at all. But for example, here I can draw a supporting hyperplane, and indeed all the set is on one side. Okay. So, and this thing didn't happen because of the non-convexity of the set, because it bends inside. So the supporting hyperplane was, so there will be some points, I'm not saying all the time, but there will be some points on the boundary where there should be. Okay, if not, then it will become convex. So for a non-convex set, there must be some point in the boundary where supporting hyperplane cannot exist, and that is making it non-convex. Okay.
Okay. Thank you.
Yeah. So Taylor expansion, as we know in data sciences or whatever field you are going to work in, you will work on higher dimensional problem. Okay. Single dimensional problem one can solve, even high school students can solve with the techniques that they know. Okay, so take derivative, double derivative done, find critical points and so on. We are not talking about that. We are talking about very high dimensional problem, and that is why we have to know multivariable calculus, which is typically taught in UG, or even sometimes people study at a higher level, right? The complicated stuff like Green's theorem and Gauss theorem and so on, right? Okay, so but this is still within our range. So let us say we want to do Taylor expansion of the function. So here I should make a correction. It should be like from R2 to R now. So I have a vector of length 2 of components x and y, and I want to do a Taylor expansion of this. So Taylor expansion of this will be is written down here, and as you can see, Taylor expansion is an infinite series, and I have not written infinite series here. Rather, I have stopped at some point. So I can say that this is like a second order approximation. So second order in means that I stopped at the third term. Okay, it's second order because we stop at the second power. Okay, so these are like, if you see the mixed power of this, then this is the second power, this is the second power of y variable. Okay, so this is the second order approximation. That's why we have an approximation here.
Hello, sir. Hello, sir.
Yes.
Sir, there is an error. It should be dou f by dou y ab y minus b, right?
Yes, this will be y here. Yes. So this will be the second order approximation, let us say, right? And then we wonder, like, what are these terms here, right? So so these terms, I think in the last class also I mentioned, these terms will be it can be written as a Hessian. Okay, so we can write this compactly as FAB plus, and I write this as a vector. So del f by del x, del f by del y. Okay, and then this is x minus a, x minus b. vector. Okay, so I'm vectorizing it, and so this is something I did last time. Okay, and then the remaining term I can write this as del 2f by del x square, del 2f
y minus b, right?
del x del y, yeah, y minus b, and del 2f by del y del x, del 2f by del y square, and to make x minus a y, so I should also multiply with this x minus a y minus b. So this is the vector times the Hessian times the column vector x minus a y minus b, and then there will be remainder terms, but as I said, we cannot keep adding things up to infinity. One of the reason is like computing this higher order derivative is costly. So typically you will be working with approximation all the time, because numerically computing up to infinity doesn't make sense. You will be lost in the for loop of just computing this terms only, right? So you will
again small confirmation. So it could be half into this Hessian matrix term, right?
Yeah, and there will be 1 by 2 factorial that is coming from the Taylor expansion. Okay, so there was like 1 by 1 factorial, but this is just 1. So that's how that's how 2 is coming here. And if you multiply this out, it will be easy enough to see that it is easy enough to see that this will be the expansion that I've written here. Okay, it is rather one can prove these results. Okay, so I can give you a very quick hint. Last time I tried to skip it. So the way we can prove this result is, let us say for the 2 variable, I can parameterize this. So remember that there was something called implicit function theorem, and implicit function theorem allows you to parameterize locally. Okay, not globally but locally. But anyway, Taylor series is about local expansion anyway. We never said that we want a global approximation of the function. We always say fx can be expanded near the point x equals to a. Okay, so if that is the case, then locally we know from implicit function theorem. So from implicit function theorem that we did, before, I can always parameterize. So I can write gt is equal to f of xt yt. Okay, so I can write this as f of xt yt, and then where xt, I can see xt as something nearby a and b. Remember, I want to do expansion near a and b. So I can locally parameterize x. So locally xt will look like a plus t x minus a, and yt will look like b plus t y minus b, right? So we have a function like this, and we have a comma b in R2. Okay, so we are saying like we can traverse a little bit. So what we are saying is like we can traverse some direction around a and some direction around b. Okay, so some direction around a and then some direction around b we can traverse. Okay, so this is giving me the small neighborhood that I'm looking for. Okay, and around this neighborhood I can parameterize the function. Okay, so then x prime of t will be x minus a, and y prime is the derivative here, is y minus b. Okay, so I take the derivative with respect to t because these are functions of t, they are parameterized now. And if we took a double derivative, then this will be 0 because there are no longer t left here. So this will be 0. Now we can use the chain rule for this. So using chain rule for let us say 1. Okay, so for 1, what we have is g prime t is okay. So how do you differentiate functions like this, right? So let me recall a little bit a general form of this. So this is of the form So this is of the form, let us say I define a function Vt is f of, let us say x1 t comma x2 t comma dot 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 comma xn t. Okay. So, or let's keep this as y. Okay. So if you don't, okay, I think this annotator is painful. So let us see, let us keep this v. Okay. So I have a function v, which is a function of t, and inside there a function depends on x1, x2, xn variables, which themselves depend on just t variables. Okay. So this is depending on t variable, this is depending on t variable, and so on. Okay. So how do we take derivative of functions like this? Okay. So you have seen so far, you may have seen so far something like this. Okay. And then let us say y is like this. So here here you have a function of gt, right? Here this is extension of that. Here is like function of x1t. So x1 is like some g, right? And then you have another function x2t. But the important thing is that it still depends on t only. And this is x and t. Okay, up to here, so this is like the chain rule. Okay, so dy by dt is f prime of g of t and then g prime of t. So that's how you do the chain rule, right? Now, so this is the chain rule that you do, but here the only difference is that you have now more of the g type functions here. Okay, different g functions, let us say x1, x2, xn. So in this case, if we want to do derivative, then you have to do so first you have to do like del f by del x1. So you take derivative of this with respect to g. Okay, so here when I'm saying f prime, it's a derivative with respect to g. Okay, so this is like df by dg, right? So this is df by dg, and then this is dg by dt. Okay, so again I will write down df by dg. This is the chain rule, right? And dg by dt. So that's why you are doing it like a chain. So first you see f as a function of g, and then you see g as a function of t. So this is the chain we are talking about. If f had more of these, right? So if f was like u of v of w, okay, of t, then the same rule applies, right? So df by du, du by dv, dv by dw, and dw by dt. Okay, you should be careful about this derivative because we will be doing optimizers for neural networks, and we will derive results on this thing. So you should be familiar with this. So these are called chain rule because it goes like a chain. You see functions as a function of intermediate variable, and then this intermediate variable and this intermediate variable. So here the chain rule more or less you might be knowing, but here it's like you have a comma here. Okay, so you have this. So what you do in this case is like you do del x1 by dt, because x1 is only dependent on t. So I can, instead of doing del, I can just do d. Okay, so partial, here we have to do partial because it's a function of several. We are seeing this as a function of several variables like x1, x2, xn, right? So here we have del f by del x2 times dx2 by dt. Okay, so this way you keep doing this, and last del f by del xn and dxn by dt. Okay, so these are the results that we have from calculus. So here we need a smaller of that. So this is just two variable case, but the idea is simple. So we have del f by del x and dx by dt plus del f by del y times dy by dt. Okay, so so this is what we have, and we can also take a double derivative. So let us go go here. So let us note down g prime ty del f by del x plus dx, oh sorry, not plus, but dx by dt, and plus del f by del y times dy by dt. Now I can take a double derivative with respect to t. And if I take double derivative, then we this is a function of t. So so it is still possible that there is a t here and there is a t here. There is a t left here. There is a t left here. So now now this is the case of like product rule will be applied, right? So df by dt is first function into differentiation of the second plus second function into differentiation of the first. Okay, so differentiation is obviously with respect to t because all are variables of t. So this is the product rule of calculus. Okay, I did not do revision of these things because I will do it along the way, right? So if I apply all this, then if I apply all this, then what I will get is the following. So I will apply the product rule, right? So if I apply all this, then yeah, so what do I get? So I get d2f by del x square and then x prime t whole square. Okay, I have done a little bit of simplification also. I'm not going into full detail of this because I have given you the hint what I have used here, del x del y and then x prime t y prime t. Okay, so due to the product rule, I will have like two terms coming. So so I will have I will get them added, and then I will have del 2f by del y square, and then y prime t whole squared. Okay. So after applying the product rule, that's what I get. Okay. So now putting t is equal to 0. Remember that we want to compute our derivative at x equals to a. So need x comma y at around a b. Okay. So to do that, I will make t tends to 0. Okay. So or exactly 0. Okay. Because I need it, the expansion I need it as at AB. So put t equals to 0. So this will imply x0 will be A and y0 will be B, and hence this implies g double derivative at 0 will be, so this will be like del f by del x, and that will be like computed at AB. And then we have x minus a because the derivative x prime was this x minus a and y prime of t was y minus b. Actually, it has no dependence on t. So even at x prime 0, it still remains x minus a, and at t equals 0, it still remains y minus b. Okay, so this is like x minus a and then plus del f by del y and y minus b. Yeah, so this is okay, sorry. So I think what I did here is the first derivative right now. Okay, so so I will never be able to change it now. So okay, so this is 0, and then I can do it also for the I can also do it for the second derivative. Okay, so so what I did so far was this, and I can also do it for the second derivative at 0. So if I do the second derivative at 0, then I can write this as a. I will tell you what is a plus 2b x minus a y minus b plus c y minus b squared. Okay, so what I have denoted as a, you can easily guess this will be this, and b will be this part here. This is b, and this is a, and this is c. Okay, so we have used these notations, and so remember that g is like a single valued single valued. Okay, so what we are deriving here is a Taylor series for the multi-valued. Okay, and assuming that for single valued, for G from R to R, that's why it's defined. So for G from R to R, I can expand G at 1. Okay. So if I do that, then I can expand I can expand G as follows. So that at G of 0 plus G prime at 0 plus half of G double prime 0 and so on. Okay, so so if I do that, then I get the Taylor expansion of the required. So what is the G1 then? If you go back and see G1, so G of 1 will be just fx, and so xt will be 1. Okay, so x at 1 will be x and y at 1 will be y. So it will be, so G1 will be fxy. Okay, so here it would be fxy is equal to feb plus G prime of 0. Okay, so here I have assumed that this Taylor expansion is okay for R to R, and what I have shown you is a Taylor expansion extended to R2. Okay, so by assuming that, assuming our result. Okay, so so we have stopped here, but yeah, one can extend this proof to do it for more variables. Okay, so here it's a plus b plus that grad fab. Okay, so those were the terms, and then you have ab here, and then plus half of grad square f, which is the Hessian. Okay, and okay, so here I have to put ab here and then ab here. Okay, so this, the full thing we will see shortly. So this is the proof of Taylor expansion in multivariable case. Okay, assuming that the Taylor variable is known in the expansion is known in the single variable case. Okay, so this is the idea behind the Taylor expansion. So
Hello,
these
sir.
are the same things that we got before. Okay, A, B, C are exactly the same that I have derived just now. Okay. These are the Taylor expansion of the higher order. I mean, definitely this is not the first order, because first order will always be a plane that we know. So this is some more higher order Taylor, or in fact, this is like a second order. Okay, so your original function is this. So this is the original function, which is more nonlinear in the sense like it can bend many times. I mean, it's roughly nonlinear means higher order nonlinearity means that it bends a lot. Okay, and this is the approximation. So this is, you can see, this is the quadratic approximation of this function at point here. Okay, so it is valued only around. You can say that it's only approximating the function somewhere closely around this region. Okay, which is maybe some point a b here. Outside this, error is not approximating well, because the function is going like this, and this your approximation is going like this. So outside the region, it is not really. But if your point AB was here, you would have again approximated it very nicely around this point. Okay, but so it's all about where you want the approximation, and then locally it will try to approximate it by a quadratic. Okay, if the function was originally linear, then definitely the quadratic term will automatically vanish, because if the function is linear, then the Hessian will vanish anyway, so the third term will never appear anyway. Okay, so it's not that it will make it always like this. It depends on the function. So function is linear, the Hessian term will be 0, or even the higher order term will be 0, so it will never bring in this, so it will end up doing this plane approximation, which is what we want, because linear functions will look like a plane, right? So so this is the approximation, and so the affine function given by this, now we know that this is indeed a Taylor approximation of the function f near the point y, okay, near x, okay. So the inequality here states that for a convex function, the first order Taylor approximation is actually a global underestimator of the function, okay. And conversely, if the first order Taylor approximation is always a global underestimator, then the function has to be convex, okay. So, and the quiz is, what does the inequality above say when grad of x equals to 0? Okay, so what will happen with grad of x equals to 0, assuming that this inequality holds? So from here, what we observe is that grad of x equals to 0, then this means that this term will vanish when grad fx equals to 0, which is here, okay. So, so what does this mean? So this means that fy is greater than or equal to fx, okay, for all y in the domain of f. Okay, so this means that at x where grad vanished, okay, so at x where grad fx equals to 0, let us say this is our equation 1. 1 implies that fy is greater than or equal to f of x for all y, right? So this implies what? This implies that fx is the minima, because any other function values are above x, okay. So this implies x is the minimum, like x is the point where minimum is achieved, okay. So so if your function, so what does this, how do we interpret this, right? So if this is satisfied, okay, let us say for a function for all x and y, let us say if this is satisfied, okay, and if there exists one x, let us say if there exists one x, let us say to distinguish that x from all x which is used here, we can say that out of all x, it is not necessary that for all x this will be 0, we know that. So but let us assume that there was one x for which grad actually vanished, then that is exactly the point where you will have this for all y. And if this happens for all y, that is telling us that x must be the minima, because that's the place where fx is taking the least of all the values, okay. So combine this, what this is saying is like first order convexity. So first order convexity plus grad f, let us say some star, okay, at some star is equal to 0. This implies x star is global minima. Okay, so it's easy to see because we have just proved this. So first order convexity plus the gradient vanishing there at some x star, let us say, that gives you the global minimum. So that's what we take from here. Okay, a function will be strictly convex if the inequality is strict. So we have talked about convexity and strict convexity. So this is not strict. Okay, so if you put a strict inequality, then it will be strictly convex. And same thing goes for the concavity. Okay, a function is concave if the negative of the function is convex. Okay, and then a function is strictly concave if the negative of the function is strictly convex. Okay, so that's how we also define concavity. Okay, so this is the first order condition, and we have not proved this yet. We have taken this for granted. So let us go ahead and quickly try to prove this this first order convexity. So what we will do in the proof is that we will start with the we will start with a 1D case, let us say. So let us first prove this for the 1D case, and this 1D case we will extend this to 2D. So when I say 1D case, then I assume that function is from R to R. And when I say higher dimensional cases, then I take Rn to R. Remember that for all our cases, not all, but most of the cases that we will consider, there will be always be R. Okay, so it will be a real valued function. Real valued, but possibly multivariable. Multivariable. Okay, these are the terminologies that people use. So this is like single variable real valued function. This is multivariable real valued function. Okay, and if it was also M, then we will say multivariable multivalued function. Okay, but in our case, for most of the cases you will see in this course, we will stick to R here. Okay, so let us consider the case of n equals to 1. So consider n equals to 1. Okay, so this will be the case when f is from R to R. And so what we are trying to prove is that, so this result now, so the first order condition now boils down to f is convex if and only if fy is greater than or equal to fx plus derivative of f and then y minus x, and this is true for all x comma y in domain of f. Okay. So let us prove this this first order condition. So this is if and only if, right? So we have to go both ways, forward implication and backward implication, right? Okay, so let us go through this. So let us prove the necessary condition. So if and only if is also called necessary and sufficient condition. So assume that f is convex. F is convex and x comma y be in the domain of f. So since domain of f is convex, okay, so remember that domain of f is assumed to be convex. Okay, so we conclude that for 0 less than t less than or equal to 1, x plus t y minus x is also in the domain of f. You agree, right? This is this form we have seen, right? So this is same thing as saying ty plus 1 minus tx. So this is the convex combination and domain is convex. So hence the convex combination will also be in the domain of f. So we have used the convexity. Okay, yes. Hello. Okay, so I thought there was a question. Okay.
Hello, sir.
Yes. Okay.
Yeah. Hello, sir. So you're assuming f is convex.
Here I am assuming f is convex.
And
yes.
then saying domain of f is convex.
No, domain of f was always convex. That is like the given part of the thing. If domain of f is also convex, that is always given. Domain of f is convex is always given to us. So f is differentiable and domain of f is convex is given to us. And then it's saying that f is convex if and only if the first order criteria holds, right? So domain of f, I will give you an example where why domain of f not being convex can make your function fail the convexity test. Okay, so I will give you an example for this. I have prepared an example for this. So domain also being convex is important. Okay, so let us first prove this result. Okay, so far we have taken xy in domain, and since domain is convex, then any linear combination we take is going to be in the domain. The domain of f is a convex set. Okay, so so by convexity of f, what we have is that the curve traced by these points in the domain will be lower than the line joining x and y. Okay, so let us write this in mathematical form. So x plus t y minus x is less than equal to 1 minus t fx plus t fy, right? So this is the line joining fx and fy, and this is the curve tracing graph going between x and y. Okay, so if we divide both sides by t, so dividing both sides by t, so if we divide both sides by t, what do we get? And we rearrange also. Okay, so if I rearrange and divide by t, so it's a simple thing. So fy is greater than equal to fx. So I send this guy on the other side. So fx plus f of x plus t y minus x, and bracket close, and then fx by t. Okay, so this is what we have, and we let t equals to 0. I mean t tends to 0. So if t tends to 0, there is no dependence on t here, and there is no dependence on t here. So the focus will be here. Okay, so this will be like fy is greater than equal to fx. Okay, and plus limit t tends to 0. Okay, t may not be exactly 0, but t tends to 0. And we recall that this is true for all t greater than 0 and less than equal 1. So nothing is being violated anywhere. Okay, t can get very close to 0, and everything came from here. So all the inequality should also hold for any t arbitrarily close to 0. So nothing is violated yet. Now if t tends to 0, our focus is here. Okay, because this guy is nothing had to do with t, right? So what will happen here, right? So if we recall some calculus again, there is something called Labital rule. Okay, so in calculus, so it's after the French mathematician, and here h remains silent in French, so Hopital. And so what do we know is that limit x tends to 0, fx by gx. It may happen sometimes that if you put x to 0 and they become 0 by 0 form, let us say. Okay, if it is if 0 by 0 form. Okay, so what I'm saying is, like, if you put x0 here and if you put x0 here, if it so happens that you get 0 by 0 form, then you apply the limit. You apply the limit after taking the derivative. Then this is the same thing. So to calculate the limit, you have to do limit x tends to 0, f prime of x by g prime of x. Remember, f being 0 at a point doesn't mean that f prime will be 0 at a point. Okay, you agree with this, right? Because the function could be something that is like increasing, right? So although the function is 0 here, but the derivative is not 0. Derivative is like this, some non-positive, right? So this doesn't mean that it will still remain 0, 0 form, right? Okay, so L'Hopital rule tells you that if you have a 0 by 0 form, then you have to take the derivative, and this will, the limit can be computed like this. So this is the equality here. Okay, so this will be equal. I'm not going into the proof of this L'Hopital rule. Okay, so but this is something I'm assuming it right now. So this is the tool I'm going to use here, because if I see here, the whole thing, numerator is my f and the denominator is my g. So in the numerator, and this we are treating it as a function of t. So if we put t equals to 0 here, then this will be fx minus fx, and this will be 0. And t, if we put in the denominator, it will be 0. So it's like 0 by 0 form. Okay, so what I have to do now is that I have to take a derivative of f with respect to t. Okay, so if I take the derivative of the numerator with respect to t, then what do I get? I get f prime of x plus t y minus x. And then this is a chain rule, right? So chain rule means that I have to take derivative of the inside u term also, right? F of u of t, right? So now I did f prime of u, and then I have to do u prime with respect to t. So if I do this, then I am left with y minus x, right? and this will go to 0 after taking derivative because there is no dependence of t. Okay, so this will derivative with respect to t will be 0, and in the denominator derivative with respect to t will give me 1. Okay, so so the limit can be calculated with this, and now I can put t 0 here. Okay, so if I put t 0 here, then this will be f prime of x y minus x. Okay, just this term will look like this. Okay, so you already saw, right? This is already the proof, right? So we had to prove fy is greater than or equal to fx plus f prime of x and y minus x, right? So this is the proof, one way proof, right? So this is the f is convex, then it satisfies the first order criteria. And the other way proof is like if it satisfies the first order, then we have to prove that it's convex. Okay, so let us try to prove the sufficient criteria. So sufficiency criteria is assume that the function satisfies 1. So assume that f satisfies. So I think we gave it yeah. So let me give this as 1. Okay. So assuming that this satisfies the first order criteria, satisfies 1 for all x comma y in domain of f. Now let us prove this. So let us choose some x not equal to y, and like 2 points should exist such that x is not equal to y. Otherwise, it's there is just 1 point in the domain, and by definition, by like triviality, it will be convex because there is no x and y to check, right? So there will exist some x and y which are distinct, and they are in the domain of f, obviously. So domain of f. Okay. So choose that, and we choose 0 less than equal to theta less than equal to 1. Okay. So remember what we want to prove is that f is convex, right? So our claim that we are trying to see, our claim is that we want to prove that we want to prove that the line joining x and fx and fy. So this is like theta f x plus 1 minus theta fy is greater than equal to f of theta x plus 1 minus theta y, right? So this is our claim. Like we are already seeing that this is our target. So let us see how we can do. And what we are given is that that first thing, right? So so the first order criteria is there, and we can just write down it, and you will see that it will just follow. So let us write down the first one. So with respect to x, this holds is greater than equal to some z. Okay, so let us say some z plus, so 1 implies, okay, f prime of z, and then x minus z. Okay, so this holds for all x and z in the domain of f, and similarly for fy, it will hold with respect to the same z. Okay, there is nothing stopping that. So this is y minus z for all yz in domain of f, right? So if we look into this, we can multiply this by theta, and we can multiply this by 1 minus theta, right? And what should I do? I need to add, right? Because theta f of x plus 1 minus theta f of y I want to get. So I will add it. So I will add this, then I will get theta f of x plus 1 minus theta f of y is greater than equal to, right? So what will happen is that the z term will vanish. Okay. So what will happen? I am supposed to prove that why it should vanish. Okay, I'm so. Oh, I think it's. I think what. Oh, the jet for us was not defined yet. Okay. I haven't defined Z yet, right? The Z I am taking is not just anything, okay? So Z is theta x plus 1 minus theta y. Okay, this is the point I was missing, okay? Theta x plus 1 minus theta y. This is the Z. And domain is convex, so this Z is still in the domain of F, so nothing is violated. And with this Z, this term will vanish. That's the argument here. Okay, why is that? Okay, remember what we want here is, so we want here is fz. Okay, so somehow things should get cancelled. That's what I'm trying to say. Okay, let's see. So I'm multiplying first one by theta, and then the second one. Let us work out, right? Let us see, does it really cancel? So right hand side will be theta of f of z plus theta of f prime of z, and then x minus z plus 1 minus theta fz plus 1 minus theta f prime z, and then y minus z. Okay, from here I know that theta fz will cancel with this theta fz. So from these two terms I know that I'm going to get fz. Now the question is whether these guys will vanish.
Yes,
what
sir,
is
they are-
f? They vanish, right?
Yes, sir.
Okay. So yeah, so x minus z, and
It would be theta x plus 1 minus theta y minus z, because theta plus 1 minus theta into x. 1.
yeah. So the question is like what is f prime of z, right? So we are
No, sir,
seeing z as
we don't need to calculate f prime of z, because that x minus z plus y minus z, that would be theta times, right? Theta times x minus z plus 1 minus theta times y minus z. This would cancel out.
yes. Okay, so what you are saying is like theta times x minus z and 1 minus theta times y minus z will cancel out, right? So let me just leave it at a place where it's easier to verify. So what we are trying to say is like theta times x minus z plus 1 minus theta times y minus z will vanish. Okay, so one of you have confirmed that this is vanish, so let us say that this will vanish. Okay, so we will be left with fz, and remember fz was this theta x plus 1 minus theta y. So this is indeed the z that we are looking here. Okay, so which satisfies the convexity. So that was like in the 1D case, it's okay. That was like the 1D case, and I think I'm taking too much time. Okay, what I will do is that I will write a block for the general case and leave it, because I also run out of scratch space. So what I will do is that I will leave the general case for the moment, because it's going a little bit more than we have to balance our time so that we do. Okay, so I will go ahead and do this second order condition. So recall that second order convexity condition was this. Okay, so this is something in the real valued case, f from R to R. And this was the way we could check the convexity. And in the multivariable case, this is how we do. Now we talk about Hessian. So double derivative of a multivariable function is a Hessian, and then we are talking. We say that it's a positive definite, because matrix, there is no concept of greater than 0. I mean, sometimes you can say like element wise 0, but matrix being greater than 0, like there is no ordering relation in matrices, so we don't talk about that because two matrices may be greater than equal to 0, but still you cannot say which matrix is bigger than the which matrix, right? So that's the problem. There is no ordering there, so we cannot absolutely talk about that. So, but so the extension of the positiveness in the real valued is positive definiteness. Okay, so it's a positive definite matrix. So assume that the function is twice differentiable. That is the Hessian or the second derivative. So they are used interchangeably. And sometimes the Hessian is written like this. It's like you do grad 2 times, right? So first gradient and then one more gradient, that becomes grad square. So it says grades exist. Okay, so first of all, we assume that the gradient Hessian exists at some point. Okay, because sometimes Hessian may not exist. Okay, at each point in the domain F, which is open. Okay. Okay, so we studied open set and convex set. So these are the things that is needed here because differentiability is defined on the open set only. So if you recall, if I define df by dx, then it is defined using limit h tends to 0, f of x plus h minus f of x by h. Okay, so this is how we define the derivative. Now, now to make sure that this limit makes sense. Okay, to make sure that this limit makes sense here, as h tends to 0, we need at least some neighborhood around x. Okay, so this means that require some neighborhood around x to define derivative. Okay, that's why then only I can do x plus h. So, and this is guaranteed in the open set because remember in the open set, I take any point in the open set, let us say close by, I can find a ball around that which is completely inside. So this concept is being used here because derivatives are defined like this. The first hand definition of derivative is this, using a limiting process. Derivative is nothing but a limiting process, and hence for a derivative to exist, we need to consider points. We can only define it for the interior points of the domain. Okay, so that we have sufficient neighborhood around the point such that this ratio will make sense, or in particular this x plus h will make sense. Okay, there are other ways of defining derivative like center differences like x plus h minus 2fx minus, sorry, not 2fx, that would be like 2 derivative, x minus h by 2h, something like this. So there are also like center difference. So there are many ways you can define a derivative, but in all cases you need some freedom around your point x where you want to take the derivative. Okay, so that's why we need this open thing. So by now we know why it needs open. So what this is saying is that the function f is convex if and only if the domain of f is convex. Okay, again we need domain convexity. Okay, and its Hessian is positive definite for all x in the domain. For all x in the domain, it should be positive definite. For real valued case, this boils down to just f double prime of x greater than equal to 0. And the condition grad fx greater than equal to 0 can be interpreted geometrically as the requirement that the graph of the function has a positive curvature at x. Okay, so if we have like a paraboloid and something like this, okay, so this is a convex function. So if I draw a point here, and then if the Hessian is positive definite, so the curvature will be always like this. Okay, so curvature will be always positive. Like here, it may not be easy for me to explain, but the positive curvature means that the Hessian is like somewhat upward. Okay, upward. Okay, so that's what it means. And if it was a concave function, then it would look like this. So at each point the Hessian will have curvature like this. Small enough approximations will look like this. So these are like the curvatures of the Hessian is downward. Okay, so that's what it means. So so geometrically it means that it's a positive curvature, and that's what we are expecting for convex function. These are like ball shaped, so at each place the local approximation should have the curvature like positive type. Okay, so let us consider some function f from Rn to R with the domain of f is Rn. Okay, so if we define a quadratic function like this, so this is the, you can think of this as a general quadratic function will look like this. Okay, and P is a symmetric matrix. So remember S denotes symmetric. And so the question is, what is the gradient of, not gradient, but the Hessian. So what is the Hessian of fx? So if you're given a quadratic function like this, what will be the Hessian, right? So here you need a little bit of again calculus, because you need to know how to take derivatives, right? So if you take a gradient of this, then remember there is no x dependence here, so this will go to 0. There is a x dependence here, but only constant is there, so q will be there at the end, plus, and then there is a term like I mean, if it were a real value, then it would have looked like x times some matrix C 1 by 1 matrix times x. It would be like cx square. Okay, but since it is like a matrix form, I cannot put C outside in this case. Okay, so but it looks like some quadratic term, so it will be something like 2 times, and then half is already there, and then px. Okay, so this can be calculated. So the first derivative will be px plus q. Okay, I leave this as an exercise assignment, I would say, in, let us say, homework 2. Okay, homework 1 is already released now. So in homework 2, I will leave this an assignment. So what you have to do in the assignment is that you consider a general matrix A11, A12, A1n, AN1, AN2, ANn. It has to be symmetric, so hence square. So rows and columns are the same. So take a general matrix and take a general component vector x. So x1 to xn are the components. Prove this result. Okay, so you can explicitly multiply rather than taking it from a book. Okay, so you can explicitly multiply x1 and multiply x from the right hand side and see what this terms become, and then what happens if you take the first derivative, and then you will get this after rearranging. So this is mostly algebra, so there is nothing deep here. If I took further derivatives, so then I have to take a gradient of the gradient. So if we take gradient, then this guy will now go to 0, and this is like some constant matrix, because the P matrix is given to us. So this is like a constant, but it's just that it's a matrix now, not just a number. And this is a vector. So if I do this, then I will end up getting P here. Okay, so the Hessian in this case will turn out to be a matrix P. Okay, so remember that what the second order condition tells us is that, so this is the function, and let us try to see what it will mean in case of a general quadratic function. So if we are given a quadratic function like this, then it will be convex if and only if first of all, it should be twice differentiable. In this case, it turns out that it is indeed twice differentiable. Second step is that the domain of f is convex. In this case, the domain of f is whole of Rn. We know that it's a convex. So the two basic criteria are satisfied. And gradient double derivative of f exists. So we have seen that it exists, like it is defined over all x. I mean, it's not getting violated in any way. So so all the things exist. So now we can apply the second order condition. So second order condition tells us that a function is convex if and only if second derivative, or in other words, the Hessian, is positive definite. In this case, we found the Hessian to be P matrix. Now everything boils down to this P matrix, right? So if P matrix is positive definite, then it becomes a convex function. So we have a very interesting criteria. Now for any general quadratic function that someone gives you, And let me tell you, in many of the research problem, you end up with a lot of quadratic model actually, especially if you deal with controls, robotics, and those kind of stuff. You will see that many functions are can be actually written like a quadratic form actually. And in that case, one of the criteria for you to check would be so by hand you will try to do obviously. So and find some expression and see that the matrix P that you are getting. Okay, the first of all you may have to rearrange things in this form. Okay, to identify what is the P matrix, right? And once you have this P matrix, from there you can immediately say whether I'm going to go for the convex optimization problem and so on. Okay. And there may be inequality or equality constraint that we have not talked about. In this case, the problem could have been minimize f of x, and it's unconstrained problem in the sense that I have not done any restriction on the domain. So when I give domain like Rn, it means like there is no restriction at all. Okay, so these are called unconstrained optimization problem. So in those cases, you may come into you may think like when it's a convex or not, because then it will give you clues of which optimizer to use. So earlier I promised that I will tell you why the domain of f needs to be convex in all the definitions that we have seen. In particular, the first order convexity we have seen and the second order convexity we have seen. And the reason is that that if we see the function this fx is 1 divided by x square, the domain of f is indeed this. The function is not defined at x equals to 0. So we have to remove that from the domain. So remove that from the domain x equals to 0 part. So only consider x non-zero, and the function is well defined. And we see that so we see that f double prime of x is greater than 0. Okay, so we see that f double prime of x is greater than 0 for all x in the domain. Okay, so if we do the f prime of x, right? So this is like x to minus 2, right? So if I take a derivative of this, then this is minus 2 and x minus 3, and I have to take one more, right? So f double prime, it will be minus 2 and minus 3 and x minus 4. Okay, so d by dx of x to the n is n x n minus 1. This is the formula for taking derivative of x to the n form. Okay, so this becomes 6 by x to the 4, and this is always positive number. Okay, because yeah, it's always positive number, and especially x is removed from the domain, so there is no issue with x here. So this is indeed greater than 0 for all x in the domain. Okay, so this is what is verified here, but it is not a convex function. But it is not a convex function. Okay, so but we can prove that this is not a convex function because this is of the form like 1 by x square. Okay, so what is the plot of 1 by x square? Right, so x, so it's somewhat, so how can we guess the plot of x square? Right, remember that x equals to 0, it is certainly going to infinity. Okay, so isn't it something like this? So x tending to let us say negative infinity, it's going to be 0, and x tending to 0 is going to be infinity. And if x goes from the positive part, also it's going to infinity. And if x goes to the positive part up to positive infinity, it's going to decrease. So it is something like this, and we know that this is not convex because if I draw a line, let us say here, and line here, it is below the function value. Okay, so it's below the function value, so it's not convex. Okay, 1 by x square. Okay, so this is an example where it tells you that domain of f being convex is rather important. Okay, now let us do, we have 3 things in hand. So the line definition of convexity. So line joining two points on the graph of the function must be above the function values. That's for the first definition, and that applies also for non-smooth functions. Provided you have smooth functions, let us say if you have first order smoothness, So if the first derivative exists, then it's called smooth. So if the derivative function is differentiable, then it's called smooth. Okay. So if first derivative exists, then we can apply first order convexity. Okay, so first order convexity, we saw that fy is greater than equal to fx plus f prime x y minus x. Okay, or the grade of fy minus x for the general multivariable function. And then we saw the second order condition for convexity, and that is very simple. You take the Hessian and check whether it's positive definite or not. So these are the three things we have in hand, and depending on the problem at hand, we will check whether it's convex or not. And moment it's convex, we will apply convex algorithms. Okay, the convex optimizer. So to do that, let us do some practice of whether a function is convex and so on. And there will be some tricky problems I will tell you, which you may actually see in actual research problems. And until you work it out, you will never know whether to apply convex algorithm or non-convex algorithm. So I will let you through some complex examples where proving convexity itself requires some trick. Okay, let us start with some simple examples. For example, exponential function is convex or not. Okay, so so what do we know about this? E to the x is convex or not? Well, I would say apply second derivative test. So fx is e to the ax, f prime x is e to the ax. Okay, that's what we remember. And then if I do double derivative, because all this exists and so on, and the domain is convex, so all this is there. So this is like a square e to the ax. Now this is positive, and this is always okay. A is like any r, right? So it's like at greater than equal to 0. Okay, so if a is 0, then so overall this is like greater than equal to 0. So this is like convex. Okay, this is like convex. I mean, it is strictly convex if a is greater than 0, then strictly convex. Otherwise, if a is 0, then obviously this becomes 1, and double derivative will be like, I mean, this is not strictly convex because this is just the flat function, so it's not strictly convex. The line joining is equal to, right? It's not greater than, right? Okay, so this is, yeah. Okay, so second derivative test confirms this, and similarly you can do this power. So now the f of x is x to the a, and here it is convex, but there are now conditions. Okay, the conditions are like it's convex on r plus plus. So r plus plus is like always like positive number. I mean, even excluding 0. So what this is saying is like this is convex when you have a domain defined to be like this, and A has also some restriction like this. Okay, so if you take a double, so fx is this. If you recall from the calculus, it may not be easy to take a derivative of this explicitly. So you may have to do the log. So let us say y is x to the a. So log y is a log x. So dy by dx 1 by y is a by x. Okay, so dy by dx is y a by x. So y is x to the a times a by x. Okay, so this is how you get first derivative. And I will ask you to do this. And if you if you do the second derivative, that I leave it up to you. That will require you to use the quotient rule, right? So how do you use the quotient rule, or you can also treat it as a product rule? Okay, so this is like first function into differentiation of the second plus second into differentiation of the first x to the a. Okay, so this boils down to minus a x to the 4 x to the a by x square plus a by x times y times a by x. And if I take x to the a common, so this is a by x whole square minus a by x square. So this is x to the a. I can take x square common. This is a into a minus 1. So this is the second derivative. Now second derivative, for this to be positive, okay, now I'm already given that x is in R plus plus. So this is positive. Okay. So this is positive number, and positive number to any power is positive. So this guy is like positive and this guy is like positive because x cannot be 0. So this is like strictly positive, strictly positive. So everything depends on this guy. Okay. So this guy is positive, is greater than or equal to 0 if a is greater than or equal to 1 or a is less than or equal to 0. So which is what is defined here. Okay, so a greater than or equal to 1 and a less than or equal to 0. The double derivative is positive, and this is when it guarantees that x to the a is convex, and it will be concave or the other way. So to make it less than or equal to 0, then a has to satisfy this. Okay, so these are the ways we can take a double derivative test. Okay, I still have some time. So we can also do it for absolute value, right? So let us try. I mean, try this absolute value. Logarithm is concave. Try this. Okay, these are very simple examples. Okay, I want to do the more complicated ones. So log x is concave on R plus plus. Try this. X log x. Okay, sometimes it's called negative entropy. So we will have some time to see why is that. So x log x is convex. So again, you can do second derivative test to check. Okay. Yeah, and here also you have to see, okay, whether you can do second derivative test or not, because this is modulus here. But then if it is given that the domain of x is in plus plus, that means x is positive. So then you can remove the absolute value from here and then apply the double derivative. Okay. So you have to do this as an homework assignment. I'm going to throw this in homework assignment. Okay. So norm is a convex function. Any norm is a convex function, and that happens because of the triangle inequality. Because if I take a norm, right, so theta, okay, so norm can be defined like this. Norm is a function, right? So some p is there. Okay, we know that p can take many types of norm are there. So what we have to prove is that theta f of x plus 1 minus theta f of y, okay, is greater than or equal to is greater than or equal to f of theta x plus 1 minus theta y, right? So in this case, this is like theta of norm of xp plus 1 minus theta of norm of fy is, yeah, this, right? So this we leave it here, and let us check the other way around. The other way around is f of theta x plus 1 minus theta y. So this is norm of theta x plus 1 minus theta y. Okay, p norm. Now we will apply triangle inequality. Okay, so triangle inequality. So you recall triangle inequality. So triangle inequality says that u comma v in Rn. So u plus v norm, okay, any norm is less than or equal to u plus v. Okay, so we apply triangle inequality here. So this becomes less than or equal to norm of theta x plus norm of 1 minus theta p. Now for the norm, we know that scalars can come out. So this is theta of norm of x p plus 1 minus theta of norm of y p, which is what we wanted here. Okay, so this is like less than or equal to. So this is less than or equal to, right? So this guy is greater than or equal to this guy, right? So that's what we have written, right? So we have proved that the norm is like on a convex. And then we can prove that the max is convex. I think we won't be able to do it today. You can already think about this, why max function will be a convex. Okay, the max of, in this case, is the max of x1 to xn Like, can you relate this to norm here? Like this is the
Hello,
maximum
sir.
of this. Yeah. Yes.
It can be LP norm,
Yeah.
like
Infinity norm.
Yeah.
Infinity norm. You are saying, right?
Yeah, yes, sir.
But remember that this is not exactly infinity norm. Why? I tell you that this is not exactly infinity norm. What was missing in the infinity norm? What
They
was?
should be bounded.
There was, isn't it that there was absolute value, max of the absolute value of the components, right?
Sir, I didn't got
Yes,
it.
sir, it is.
Yeah. Yeah. So you recall that the infinity norm is max of, because norm has to be positive, right? So the norm, the way norm is defined is like absolute value of x1 and x2 and so on.
Yeah, yes, sir.
Xn, because norm has to be positive, norm must be positive, so that's why we need absolute value. So but here we don't have absolute value, so this is slightly different. So otherwise if it was mod here, then we could have used the previous result and say that norm is convex, so this is convex, but this turns out that this is not. So there are some additional conditions. So I'm claiming that this is without norm also, its max function is convex. So this is something we have to check. In the meantime, you can try always. You can always go ahead of me. The best students always would like to do things on their own, right? So you can think ahead and see why it should be convex. So anyway, so I have to stop here. So I'm going to stop the recording, and I can continue the discussion if you want. But first, let me stop the recording.
Hello, sir.